Okay, so this radiation exchange is occurring. Where does that t to the fourth come from? So let's talk about that next. This is sort of the step one in understanding where the rate equation comes from. Step two is something called blackbody emissive power. So it turns out the maximum power emitted from a surface, is the following equation. So let's write it as a heat flux. Let's write it as Q dot divided by AS. So we could also say Q dot double prime. It's a area-specific heat flux. That is equal to sigma times T to the fourth. Right, again, where sigma is 5.67 times 10 to the minus eighth. Units are watts per meter squared, Kelvin to the fourth, or Stefan Boltzmann constant. All right, so this is sort of, I don't know how you, where did this come from? Well, it turns out that this is actually sort of observed. Like this is empirically observed that if you're looking at radiation heat transfer, the radiation heat transfer scales to the absolute temperature to the fourth power. So remember that the units on this have to be in like Kelvin, right? Absolute temperature. Some things that are assumed here. So sigma T to the fourth assumes. It assumes that we're accounting for first emitted power over all wavelengths. So this is called total spectral. It's total spectral. So when I say like the total heat transfer Q dot, that is sigma T to the fourth, that's all radiation emitted. So as you'll see later, the radiation that's emitted at a given wavelength varies, right? So if you're the sun, you're going to be emitting very high frequency radiation. If you're you sitting out in the room, it's much lower frequency. So there's this sort of spectral dependence. If we integrate up that entire thing, that's sigma T to the fourth. So it's emitted power over all wavelengths. The second thing that we assume here is that this is, I'm going to use the double quote, emitted power over all directions. Okay, and this is referred to as total hemispherical. All right, so the idea here is it's possible that if I'm standing here looking at the wall, the intensity of the light I see, if I could see the wall emitting radiation, might be different from the intensity that you would see sitting over there. Right? So there's like this directional dependence, potentially, of light emitted from a surface. So when we say sigma T to the fourth, we're assuming let's integrate over the entire dome around the thing that's emitting, total hemispherical. All right, the third thing is emissivity is, let's say, epsilon equals 1 at all wavelengths. Okay, and this is what we call a black body. Okay, so something that's a little confusing. So we're talking about emissivity, all right? Emissivity is the ability of a surface to emit light. So, okay, or you look at something that's gotten really hot, like a piece of iron in the fire. It's starting to emit light. It's getting hot enough that you can see it. There may be some sort of modification that, excuse me, that a given material has on that ability to emit light as a function of wavelength. So like if you're looking at a piece of metal, if you're looking at a piece of paper, if you're looking at some other material, some pure, like say hydrogen or something like that, they all have like different ability to emit radiation as a function of wavelength. What we're assuming with sigma T to the fourth is that it's this ideal surface. something called a black body. And why do we call it a black body if we're talking about emitting light? Well, it turns out that the emissivity of a surface is equal to the absorptivity of the surface. Right? And we'll give some nuance to that later, but that means if epsilon is equal to 1, then absorptivity is also equal to 1. That means it's absorbing all light coming in. All right, so that's why we call it a black body. So these three assumptions are sort of baked into this sigma t to the fourth. Then we actually use the equation, we have to modify it. So we start with sigma t to the fourth, multiply it by area. Now we have to multiply it by epsilon to get the non-black body effects. Okay, yeah.
What are some properties that alter the emissivity of an object?
Yeah, so the question was what can alter the emissivity of an object? So if you think of like, okay, well, let's give some examples. So if you look at the grass, it's green, right? The grass plants have the ability to reflect light that is green. So for whatever reason, their chemical structure is such that when green light hits it, it doesn't absorb, it bounces off. And maybe that's like the spacing between the atoms in the molecule, the way that the proteins are folded or whatever, it just sort of naturally reflects that light. So it is selectively reflecting a particular set of wavelengths. Whereas, okay, the dirt next to the green leaf is very different, right? It has different characteristics. So it comes down to like the kind of the way that the electron, excuse me, the way the electrons kind of respond to incoming light at different wavelengths. Okay? Other questions so far?
So if emissivity equals 1, would that mean that our eyes would perceive this object as white or as black?
Black, purely black, right? No surface exists that has emissivity of 1. You can get surfaces that are emissivity of 0.999, and they look very, very black, but there is no actual black body. Right? Well, maybe I'll caveat that a little. There are some things that behave like a black body. Cosmic background radiation, right? You've seen that, the map of cosmic background radiation? That's a black body, basically. Yeah.
So does like reflective energy not count in the radiation?
Yeah, so if you are reflecting energy, so we'll get into this energy balance on reflected surfaces. That's a different level of detail that we're going to get into. Right now, what we're talking about is just from emitting. Basically, the emissivity of less than 1 will cut back on the amount of heat that's being lost from a surface. So like, yeah, if you take emissivity of 0.5 and you multiply that by your sigma t to the fourth times area, it's reducing the amount of heat that's being lost from radiation from that surface. Okay. Anything else? Okay, so here's the definition of radiation. Radiation is energy transfer to or from a surface via electromagnetic waves. So this is, like I said, different from conduction, different from convection. You're not moving stuff. You're not transferring adjacent, from one adjacent thing to the next. It's energy transfer from a surface via waves, light waves, and it can propagate as far as light can propagate. So this can happen, well, first of all, we typically capture this, excuse me, as a surface phenomenon. Meaning, normally we think about the radiation flux from a surface, not from sort of generated inside a body. So like you're not experiencing radiation that's being emitted behind the wall. It's from what's at the surface of the wall and the temperature at the surface of the wall. Does that mean that there's no radiation happening inside the body? No, there is still. It's just that it is absorbed by adjacent stuff by the time it actually gets to the surface, and it's really only the surface stuff that's emitting that you experience. Okay, it's a surface phenomenon. It is non-local, meaning radiation over there can affect me over here without being in contact. Another way of saying that is it can travel through vacuum, V-A-C-U-U-M, just in case you're wondering about that. Vacuum or transparent media. Okay? So you don't need something in between to be a medium for heat transfer. And then the last thing is that the power of a, say, I don't know how to say this, the power of like a ray, we'll put that in quotes, a ray of radiation is related to the electromagnetic EM frequency. Okay? Higher frequency, more power.